Okay, finding the area between curves expressed as a function of x. That's section 8.4 from the AP. If you have not done the do now yet, pause this video and do it right now. Otherwise, I'll give you the answers. Let me just go in here like that. That's answer number 1, finding the area that you're given the function, the boundaries from 0 to 4. And for 2, looks like that. Area under g of x, and then the boundaries from 0 to 4 as well. Now, if I'm finding the area, that's just finding the area under one curve with respect to the x-axis. If I'm finding the area between two curves, instead of relating it to the x-axis, I'm relating two curves to each other. There are two ways you can think of it. One way is to find the area under the upper curve and then subtract the area under the lower curve from it to give me the area between the two curves. So I use the two curves from the do now to help us do that. So in the area in the upper curve minus the area of the lower curve gives us the area between the two curves, basically composite figures from geometry. So in our case here, I found the values in the do now, so that gives me 44 over 3 minus 20 over 3, which is 24 thirds, which is 8. So the area between these two curves, so the area that I'm finding in here, that I'm right there, between the two curves, then is we're able to find them. The key for this, though, is just to know what the upper and the lower curves are. Another way we could think of it is just like we did when we found the area under a curve with respect to the x-axis, is to add up the the rectangles. So if we look at these rectangles, each of the rectangles, the width is going to be dx, but now it changes what the height is. Instead of just being f of x, now we take the upper minus the lower, g of x, is going to give me the height of each of those rectangles. So therefore, in our case, we could also just think of it as an integral, because that's how you take the sum of a bunch of rectangles that are infinitely many rectangles in a limited amount of space becomes infinitely thin. Literally the same way, except the height being just f of x is f of x minus g of x. So in this case, we have f of x minus g of x is the length of each rectangle, dx is the width of each rectangle, and therefore, to write the integral, we're just taking the length, or if you want to think of it as the height of each rectangle, that's fine too, bounded from 0 to 4, and then you just integrate and find the same value. Explaining why both methods work. Well, one method, if a function is below the x-axis, of why it still works, if both curves are above, or one is above and one is below, you just get a negative area underneath. So when you take an area, a positive area minus a negative area, the two areas end up adding together. So if I have something like this, for example, if I have this, here is one function, and then the other function down here below, this area is positive, and this area is negative. So you take a positive area minus a negative area, becomes a positive plus a positive. So essentially, you get the full area under, you end up adding these two areas together at the end of the day. So it still works if some of the function ends up falling below the x-axis. It accounts for that. So therefore, you don't have to worry about where it is with respect to the x-axis. So that's what I have here. A positive minus a negative ends up being a positive plus a positive, and the area above the x-axis is increased by the area below the x-axis. Create a general formula for which the area between two curves. Okay, the area between two curves can be this. I put in an absolute value, otherwise you would have to determine which function is above the other, and we just want the length between the two curves, so you could put in an absolute value. If you know which function is above, I would take out the absolute value, or else you have to account for the absolute value when you are doing the integral, right? You have to account for what's above and what's below, so you have to be a little bit careful. It lets you avoid having to determine which one is the upper function and which one is the lower function. So it makes your life a little bit easier. But whenever you have absolute value and integration, you have to still be careful when you do that, because you have to account for where is it, whatever is inside the absolute value positive and whatever is inside the absolute value negative, and separate those two things from each other. So, I mean, at the end of the day, you end up doing the same thing. But this is the general formula that always works for the area between two curves bounded from A to B. All right, let's try some examples next. I'll make a new video.